Okay, these can be challenging Alex problems when we're dealing with the Arrhenius equation, and a little bit challenging just kind of understanding and the setup, but it's also can be just a little bit challenging in the math, where you just have to be real careful in the math. And it says this, that the rate of some reaction is known to obey the Arrhenius equation, and it gives us an activation energy right here of 45 kilojoules per mole, and gives us a rate constant at a temperature of 106 degrees C, and it asks what will that rate constant be at 44 degrees C. Okay, well, the Arrhenius equation states this, that the rate constant is equal to some frequency number, and then that is going to be multiplied by E raised to the minus EA, this is just the Arrhenius equation, divided by RT, where R is a constant. They give us EA. Temperature, we have two different temperatures where we could calculate K, and then it's this frequency factor that we just don't know. So what can we do? Since A isn't given, well, we can set up conditions where A cancels out, and so we'll call the 44, the conditions of 44 will be our K2, and whatever the conditions are at 106 will be our K1. And so we can say this. We can say that K2 equals, so K2 over K1 is going to equal then some frequency factor multiplied by E raised to the minus E A divided by R. This is going to be T2, and that is going to equal A E to the minus E A divided by R T1. Well, if I set it up like that, then that A is going to cancel out, and so I then can have K. So let's just look at this actually real quick before I write this down. Is I don't know what K2 is. That's the rate constant at 44 degrees C. I am giving a rate constant at 106. That'll be my K1. I know what E is, I know what the energy of activation is, I know what R is, and I know what T2, and I know what T1 is. So now I just have the one unknown. Okay, so now that I have that, I can actually, just by the law of exponents, I can arrange this a little bit differently. So I can say that K2 divided by K1 is going to equal then E raised to the minus EA over R multiplied by the quantity of 1 over T2 minus 1 over T1. Okay, so I've just rearranged this equation over here using some exponential laws to rewrite this to look like this. And I would kind of, I don't know if I'd have this memorized, maybe I'll give this to you on a test if we use this, but I would then know that this can be reduced to this. Maybe you can do the math yourself, but if not, I would just memorize this equation right here. Alright, so we know that our R value is going to be given in units of degrees Kelvin. R is a constant, so R is going to equal 8.31446. That's going to equal joules. So notice how my energy activation is in kilojoules, so I might want to get that into joules. So joules, and that's going to be mole minus 1, and that is going to be degrees Kelvin minus 1. So I need to be in degrees Kelvin, and I need to make sure that I am in kilojoule. I'm in joules as opposed to kilojoules. Okay, so now let's go ahead and convert our temperatures from Celsius into degrees Kelvin. So T1 is going to equal 106 plus 273.15, and that is going to equal 379.15. So 379.15. T2 is going to equal 44 plus 273.15, and so that is going to equal 317.15. So 317.15. Okay, so now I can substitute those into there as I need to. I can substitute R into there, and for my EA, then I'm going to want to convert that into joules. So I have 45 kilojoules per mole, and I know that there are, in 1 kilojoule, there are 1,000 joules, and so this is going to equal then 4.50 times 10 to the 4th joules per mole. And my handwriting's getting worse here. Okay, so now I made these conversions, I can just start substituting in here. So I have K2 over K1 is going to equal E raised to the minus EA. So that's going to, let me take that EA, and it's going to be 4.50 times 10 to the 4th divided by my R, which is going to be 8.3144. Let's keep our units in here. That's joules per mole. And 8.3144 is going to be in joules per inverse mole per inverse degrees Kelvin. Okay, and then that's going to be multiplied by 1 over 317.15, that's T2, or 44 degrees C, minus 1 over T1, which is 379.15. So that's 379.15. Okay, so you can see that's kind of some hairy, it's not the worst math in the world, but it's not my favorite math in the whole world. And so when I do this math, and I just did it on a separate piece of paper, this exponent portion, okay, of all this up here, that exponent portion right there, comes out to equal 2.791. Okay, so when I do this math, that's what I get, is 2.791. Remember, we got that minus value still out in front of there. And so if I do this, I have K2, which is really K at 44 degrees, that's how I'm going to denote that, divided by K at 106 degrees C, is going to equal E raised to the minus 2.791. Okay, and so now I have K at 44 degrees divided by K at 106. If I do that math right there, that's going to equal 0.06139. So I have this ratio. I've solved that ratio on the right hand side. So I don't know what K of 44 is. That's what I'm being asked to calculate. I do know this K of 106 is given to me up here at this 63 inverse molar inverse seconds. And so now it's just a matter of rearranging. So that is going to then equal, so 0.06139 times, just going to grab this number right up here, times 63, and it's going to be inverse molar. I have to write small inverse seconds. And so K at 44 degrees is going to equal, after we do all that and account for sig figs, 3.9 inverse molar inverse seconds. And so this is how we're going to tackle these problems. We're going to set up this ratio. We're going to ratio two Arrhenius equations together. Okay, this allows that A value to cancel out. As I said, we have one unknown at this point. We don't know K2, that's what we're being asked to find, but we know K1, we know T1, we know T2. We're given EA, the activation energy, and R is this constant that we've discussed. And so if I'm tackling this, I might even start at this equation right here. That would likely be the place where I start. And just say K2 over K1 equals E sub A divided by R multiplied by this quantity right here. And I would start my math right there. And that will get us down to where we have E. Remember, we're solving for this exponent up here. That will leave us E raised to whatever we computed right here. And then it just becomes very, very simple algebra after that. And so we can talk about this more in class, or we can do some of these together, but this is how I would tackle that problem.